You're good. On. What's it called? Occupation is 19.
Yeah, some of carbon. Yeah. We've been developing, maybe let's do this. We worked on at NYU. Climate action on where we were interested in sometimes like competition or agricultural work. We held a workshop last August, and we're trying to bring people in. We reached out to a whole bunch of but it was a group in the end. But the idea being that the policies, how much land we devote to the forest or society. We're not going to change it's like these policies are not. Each other and so you wind up.
But I think that's
I found out that it was 15
a lot of these
minutes, 10 minutes. So I saw the
maybe combine
just made my Michigan.
cultural practices that are more carbon sequestering. Okay, so like
That's
just you either choose between reforestation or solar, like a community size. So then how do you optimize? So this is the kind of at the moment.
Excuse me, c'est toi, tu donnes le deuxième tour. C'est pour ça que tu voulais, j'avais pas compris. Mais tu veux me présenter de là, en fait, je me partage, c'est bon. Ah, je croyais que tu là, en fait. Ah, bah, excuse-moi. C'est bon.
Oh, you think John? Yeah, Ben John.
Ah, yeah, Elisa? Yeah, you're here, okay. And Robert?
Yeah.
Oh, okay.
Yeah, exactly.
And Toshiro.
I mean, the trade-offs are fascinating. How you actually do that trade-off analysis, like how do you value that biophysically, and then how do you actually do the economic trade-off analysis? It's fascinating. Neat, yeah.
Okay, we will start. Online, could you tell us, please, if you are hearing us? Can you hear?
Yes, we can hear you.
Okay, thank you very much. So we're going to start with a bit late, coffee break. So my name is Pierre Mart. I'm working at INRAE in France. And I would be sharing this this session, although I'm not so specialized by any means. But okay, so today we'll have I think 7 talks. We have a slight change in the program. Nathan Chobik, the first speaker of the conference in his agenda, so he will actually be the last speaker of the session. So Umia will start. So I'll let each speaker to introduce themselves because I didn't receive any information. So if you want to introduce yourself, and you could, if you want, use this to advance the slides. Yeah, it's there's a lag. bottom.
The clicker is working. See the clicker.
Good afternoon, everyone. So I'm here today to present our work, the assessment of soil variables' relative importance for cereal yield predictions under rain-fed cropping systems in Morocco. My name is Umnia Naji, and I am a PhD candidate at Mohammed VI Polytechnic University, working between two colleges, the College of Computing and the College of Agriculture, hence my two supervisors. So when we talk about predictions, we always think about climate change. When it comes to agriculture, indeed, climate and rain, especially in Morocco, where most farming systems rely on rain-fed, we tend to forget that, yes, climate plays an important role when it comes to agriculture, but it's when we talk about climate change, we think about drought, but sometimes we forget that there is another part of climate change, rain. But in Morocco, historically, we are a very semi-arid and very dry area. But what happened last month just was an outlier of the actual climate data set, is that we had sometime by mid-March, we had generous, strong rainfall, up plus to 88% versus last year. But when we talk about climate predictions and or predictions in general in agriculture, that's the first idea that comes to our mind: climate, rainfall forecast. We tend to forget that there is another part that plays an important role in agriculture. That's the soil. So that's the side I want to talk about today. So we see nowadays there is a lot of implementation of machine learning and AI in every different field. So this digital transformation is evolving in parallel with artificial intelligence systems. It's growing at a very important rate. But in the area of nutrient management, it's possible to integrate and interpret various pieces of information that have never been explored in this purpose. When we say AI again in soil, we think about remote sensing and drones and different types of data, but we tend to forget the important or the very first soil sampling that was happening right before. So there is a need an accurate diagnosis of curing crop nutritional status and nutrient requirement that plays a critical role in overall farm management and impacts not only the environment but also the economic stability of various farms dependent on the scales. So there is a need of accurate diagnosis that would directly benefit farmers and also researchers. So modeling soil and climate interactions is indeed crucial to predict yield and managing resources to adapt to climate change. So machine learning could possibly help us uncover these dynamics that happen in the soil that we rarely tend to give importance to or pay attention to. So hopefully this technology or this tool could help us improve decision making in precision agriculture. So lately, the use of machine learning models have been increasingly used to predict crops. Explainable machine learning tools could help us again to detect these impactful variables to be able to generate a better data for future models. So, for example, that's a study we published last year where we did a comparative study of different machine learning algorithms with different baselines to select the best performing ones on the same data set. So the research questions are: can XI methods or explainable AI methods accurately reflect the nonlinear relationships between the soil variables and cereal yield in rain-fed system? Again, rain-fed, because in Morocco, we mostly rely on rain. How can XI methods help identify key soil variable interactions that are not easily detectable by traditional statistical analysis, and how could XI enhance the interpretability of machine learning models for decision makers in precision agriculture. So our methodology was very simple, where we collect field data, and after, of course, pre-processing it, we tend to use a machine learning model to get a yield prediction. Once we get good accuracy or good results when it comes to yield prediction, then we proceed to the next step where we use the XI methods to select just the important variables. After that, either we get to the point where we have logical explanations or good explanations, or we can continue with the loop to optimize these results with the consultation of an agronomist that could help us. Are these predictions and these results that we had were good or bad? If they're bad, we have to do the loop again with more tuning. So talking about the data that we use for this study, so we had access to data that was gathered from field with accurate soil sampling methods, state of the art, how they are supposed to do, how they're supposed to be in situ, for 3 different growth seasons, from 2018 to 2021, for 8 regions and for 3 crops. Wheat, soft wheat, durum wheat, and barley that are mainly produced in Morocco. So if you are wondering why we have the soil sampling only in this particular region of Morocco, that's the crop mask. So mainly the farming happens in this particular region. For this data set, we had also 34 varieties, and mostly, as you can see a huge difference when it comes to the water regimes. The rain-fed has most points than the actual irrigated. That's why we went with the rain-fed. So for this result, for the results, so we had at this point, following the previous workflow, we just used all the data, the data set with all the three crops, just to test preliminary if machine learning could give us a good result. Again, we did a similar comparative study with different machine learners, and we selected extreme gradient boosting that gave us the best accuracy, as you can see, the visually actual and predicted yield. So we checked this step. The second step would be understanding these variables that are impacting the yield, again, mostly on soil. So we moved on explainable machine learning methods, such as partial dependence plots, that revealed that soil properties and fertilization influence literally directly the yield, where we can see here that nitrogen in top dress fertilization and K2O in basal fertilization and P2O5 in basal fertilization impacted directly the yield. So these variables show the clear impact, while other variables that could link to like micronutrients wouldn't be detected in the algorithm. Moving forward with more explainable machine learning methods, where we did permutation feature importance to dig deeper in these soil features, where again nitrogen and K2O, MgO, the number of top dress, and of course phosphorus gave the best results. On the other side, again, that's another method of explainable machine learning. That's SHAP value, where we can clearly see that the higher impacting variables of yield were mostly soil variables. Even if you see here region phasmicness, but even if it's a region, that's a proxy for soil texture and soil soil podology, because these regions are well known for having great enriched soils for agriculture. So this set of features could be categorized in 3 main categories: the ones that had higher impact, a positive influence, and negative influence. So if we select our variables of interest, we can see that the ones that had a direct impact on the model prediction and on the yield predictions were mostly variables, as I said, related to soil, like nitrogen in top dress, K2O, P2O5, also in ppm. That's the actual P2O5 that is present in the soil. So once we were able to validate this, we decided to take it a step further and do it this time with each crop separately. So unfortunately, the data set that we have didn't have a very good distribution when it comes to crops. So we can see that soft wheat, which is mostly grown in Morocco, dominates the data set, while barley and durum are underrepresented. That's the distribution of the yield per crop and per random split and temporal spreads. You can see that in the temporal spreads, we have some inconsistencies. So to deal with this problem, we did what we call SMART, where we augment data. That's the initial data, and that's the augmented data to be able to train different models and different optimizers, this time not only to predict yield, but to give fertilizer predictions. So I don't want to. These are just details of what the fertilizer recommender system results gave when it comes again to feature importance. That's just one example, but we did this on several algorithms again, and we can see that latitude, province, all of those are impacting directly the predictions, and they act as proxies of soil and climate. So more on the explainable variability of our algorithms, and this time for the fertilizer recommendation systems, we tried different sets of optimization methods just to select which one would give the best explainable for these 3 variables, the NPK, and for each crop. So we did a 3D visualization of the nutrient interactions, again, just for the 3 major important nutrients NPK. And we can say that balancing, for example, for each crop, we can say that balancing nitrogen, potassium for barley could help us improve the yield. Phosphorus would be a solution for durum wheat, and maybe optimizing potassium better would give us a better results for soft wheat. But these are just, as you can see, preliminary results that give us an idea of the effectiveness of advanced optimization methods, such as, for example, simulated annealing, that could enable us not only to give great yield predictions, but also tailored fertilizer recommendations with feature enhancements. So here comes the challenges. And again, as every machine learning researcher, we have data availability problems. There is a problem of data availability. Most of it is not open access. And there's also quality issues. We keep saying, I need data. Do you have data? Do you use data? But we never actually define this term data. What do we actually need? So probably there is for future projects or future challenges to have a good practice guide to identify, if we want to do, for example, crop yield predictions, what would be the ideal data set? That's just an example of how accurate the existing land cover maps for agriculture, for example, in sub-Saharan Africa. And we can see that there is a lot of error and biases from the beginning in the data collection. So what's interesting to work on next? Maybe identifying soil compounding drivers of yield in current crop models in different geographical regions or on a bigger data set. I'm wondering if you know about some good data that we could use, and maybe also the impact of soil physical properties and water dynamics and their contrasting management regimes on yield. As a fertilizer scientist myself, I would prioritize this one. And if you have some ideas, please come talk to me. And if you have some thoughts, please share with me. That's my email. Thank you.
Thank you. So we'll take one question. Yeah. Or yeah. Joel first. Almost at the same time.
Yeah, you didn't mention climate as a predictor anywhere, the rainfall. Is that, did I miss something?
It was indeed taken into consideration. So the data that we had just field data, but we had to merge it with climate data, just like temperature, solar radiation, Shannon index. We had to do this, but mostly we did this from Ag Era. And we are at some point in our lab discussing the fact that we want to use some local generated data from Meteo Morocco, where we could buy this weather and climatic data that was generated on Morocco to do the testing of these models.
But for the machine learning, when you chose your predictors, you used only the soil?
No,
And
just
you
for
said-
this.
and you said region.
Yeah, for this presentation, I only highlighted the soil part, but we did integrate the data set with obviously with weather features such as temperature at minimum, at maximum, solar radiation, Shannon diversity index when it comes to rainfall. They, even if they were not mentioned on the slide, but they were taken into considerations, obviously. Last AgMIP9, I presented a work when we investigated the weather features impact on yield prediction, and we realized that there was a huge difference on accuracy with and without the weather data.
Thank you very much. Antoine, you want to move here or you want to simply go? Here. Okay. So that looks like an AgMIP author list. Yeah.
Here as well. Can I, okay.
You want to see on the screen?
Yeah. Look at the people. So perfect.
Oh.
Hi everyone. Thanks for being there. So I'm Antoine Codel, an agronomist from CIRAD, and I'm going to present a work we have been doing in the last few years with a large team of people. I will not present them one by one, I take the whole presentation, but it is a low input system group. And I'm going to present some results about the effect of soil fertility loss versus the impact of climate change on maize yield in few sites in sub-Saharan Africa. First, a bit of background. So we have, as you know, some problems of food availability issues in sub-Saharan Africa. For example, maize demand is expected to increase by more than twofold by 2050. On this plot, what is pretty striking, you can see here in red, you have sub-Saharan Africa, in other colors, all other continents. And you can see that yields in sub-Saharan Africa did not increase much compared to other continents, but it was at the expense of an increase of harvested areas and then at the expense of shrubs or forest or natural areas. Yet, I mean, we could think that the climate in sub-Saharan Africa is not good enough to increase yields. Yet it's not true when we look at the result of the global yield gap atlas here, those maps from the three main cereals. You can see that for maize, millet, and sorghum, we have huge yield gaps. So the yields enabled by climates could be much higher than current yields in sub-Saharan Africa. On top of those problems, yet climate change is threatening food production. So here, for example, you have the mean change that would be expected with climate change. So you have in quite a big area in Africa, we expect more rainfall, but in West Africa and in Southern Africa, we would expect less rainfall. Then we have also a change in extreme events. Here I'm plotting just a number of droughts that could happen. Follow a bit the pattern of the change of rainfall, with more droughts expected in Southern Africa and West Africa. Then when we combine those two effects, we've got some results from the GGCMI groups, from colleagues, and they show that in West Africa or most of the countries, we may expect a yield penalty due to climate change. But as you can see, in Southern Africa or East Africa, there are still a lot of uncertainties of what could happen with the yields with climate change. So there is a climate issue, but one of the main issues that was limiting yield with the yield gap analysis is soil fertility. So there is a decline in soil fertility in overall in sub-Saharan Africa due to few reasons. The first one would be the low use of fertilizers, either mineral or organic fertilizers. Shortened fallow periods to do more croplands, but also soil erosion. So usually we talk about one solution, what we call integrated soil fertility management. That would be the use of both organic and mineral fertilizers to try to increase yield on the long term due to the increase in soil fertility. And usually we say it's a non-regret climate change adaptation because you can increase yield even if climate change will have an impact on that. Yet when we do experiment on that, we need long-term experiments. It's costly, time-consuming, so we need modeling to try to check if soil fertility management with the use of fertilizers is a good option in face of climate change. So what we are looking at is the impact of climate change on soil fertility, on the indirect impact on crop yield. It's also the direct impact of climate change, and we want to see what is the relative importance of those different arrows and what would be the interest of adding organic and mineral fertilizers. And what is a bit different compared to most modeling studies we have seen so far, that's usually studies focusing on climate change in sub-Saharan Africa. They are almost only looking at this part, like the direct impact of climate change on crop yields. So this is super useful. But for us, we want to try to check what happens with soil fertility. So for that, we needed to calibrate soil crop models with long-term experiments. So we looked at 4 sites with different soils and climates. So we needed like experiments from 10 to 20 years to have change in soil organic carbon. And we're quite lucky because those experiments had very similar treatments with the addition of organic and mineral fertilizers, but also with no input treatments. With also, as you can see on this plot on the right side, with different soil fertility, soil organic carbon initially. So then we gathered a group of 16 different crop models, soil crop models, I would say. And then we ran, so we calibrated the models. I will not show the results of the calibration, it would take too long, but once we made sure those models were calibrated on the experiments, we run what we call the sensitivity analysis over 30 years with 3 different ways of doing the modeling. So the first one would be to check the climate change only, the red part here of this plot. When we run the model for 30 years with a reset of the soil each year. So then we didn't account for the loss of soil fertility. Then in green, you have the simulation with soil fertility decline only, when we didn't run any climate change scenarios, but we were running the model over 30 years with, we would say, in a continuous mode with the soil from the previous year be used for the next year. And then in blue, you have the combination of climate change and soil fertility decline. I'm going to use the same color codes over the plots. So then if you look at the results, so this is the results over the 4 sites. In green, you have when you have only the soil fertility decline. We've seen that it's one of the main reasons of yield loss. So you lose almost 25% of the yield. In red, you have only climate change. So the size of the box would be the results of the different models. So you see some models are predicting yield loss, some models are predicting yield increase with some increase in temperature. This is mostly due to the fact that we have high altitude sites, so for example in Kenya, and then it would be more interesting to have warmer temperature on crop yields. And then when you change rainfall plus 20% or minus 20%, you also have a high uncertainties with the different models. But our conclusion here is that the impact of soil fertility decline is higher than the impact of climate change on those sites. Then it's not for you to look in big details on these plots, but if you look at the different sites, one line would be one site within different patterns according to the different sites. If you look at the second line, the site in Kenya in Embu had the highest soil fertility at the beginning of the simulations, and then you can see that it has the lowest yield penalty with the soil fertility decline, because soil fertility was still quite okay after 30 years because it had a very high soil fertility at the beginning. But on all other sites, this green box plot has a strong impact on the yields. Then we looked directly also at the impact of climate change on soil organic carbon. It was a bit surprising for us because we had the hypothesis that climate change would impact a lot soil organic carbon dynamics over 30 years. Here, this bar plot is in blue, it's no climate change. So you have in average over 30 years, like more than 20% of carbon loss. And you have the climate change scenarios in red. So when you increase the temperature by +2 or when you change rainfall. So the effect is not so strong. We could have expected like a carbon loss with increase of temperature or with increase of rainfall. It was not so much the case. And you can see the trends over the 30 years on the different sites. So you see the red line is always quite close to the blue one, where you don't have a climate change. So that's also well, maybe I come back. Yeah, that's also why we don't see a lot of difference between the blue box plot and the green box plot, because there are few interactions of climate change with the soil. Then, if we look at what interested us as well, this adaptation when we have organic and mineral fertilizers, when we add manure plus mineral fertilizers. Here, we are looking at the yield change when compared to no input systems. So with organic fertilizers, we increase yield by almost 200%. So it was expected, a big increase of yield. Without climate change, and then when we add climate change, you see we have an interaction between climate change and the fertilization patterns. Still, we don't have a big loss of yield with climate change when we have fertilization. So that's why we call that a non-regret adaptation, because you have a decrease of yield, so it's not a true adaptation to climate change. But still, I mean, it's the effect is not so strong. I think this is the last results here. If we look over the 30 years at the different sites on the different climate scenarios. So here again, the y-axis is the yield change compared to scenarios without any input. You see that over time, we have an increase of these benefits of the organic fertilization, because you build up soil fertility, you build up soil organic carbon over time, or at least you are not losing it compared to no input. So then the difference between not using fertilizers at all is increasing over the years. So last slide. We conclude that there is a significant impact of soil fertility on crop yields. Usually on climate change studies, it's not taken into account so much. We see organic and mineral fertilizer as a non-regret adaptation. So we still need to see how much of those fertilizers we can put in reality, especially organic ones. So yet we conclude that soil fertility dynamics is a bit more important than climate change. But our models are not taking much into account climate extremes, so they still need to be improved on that. The combination of climate stresses, like a heat stress with the drought, but also the impact of climate change on soil structure is not taken into account. For example, we are not accounting for soil erosion. So the impact of climate change may be much higher than what we were looking for in this study, but we are using models as they are so far. Thanks a lot for your attention.
Thank you. Okay, we were first, but he was waiting last time.
Okay, maybe I'll not take much time. Because your carbon is declining very sharply. You did not keep any root biomass or anything in the model, because what I'm asking is, in my all my modeling work, I never have it this negative carbon dynamics. This all is declining, and your decline is very fast. 100 to 60% in 30 years. That's too fast for me.
Yeah, that's very
That's it.
fast. That's there's few reasons. First, above ground biomass was removed.
Maybe you remove root also looks like.
No, we didn't remove roots.
Otherwise, negative.
We didn't remove, but the
Huh?
sites. Some,
Very
yeah, you
fast,
can.
huh?
If you
Yes,
want.
I was involved in several of those experiments.
Okay.
This is based, he didn't show the calibration, but
It's
this
based
is
on
based
true
on
data.
measurements. So this is reality of. This is
Actually, I never have
That's
seen
centimeter.
the negative
But we
carbon. Huh?
are in a situation
Okay.
in Africa where often these experiments are put after native vegetation. So we start with
Very
a
high.
relatively high,
Very high.
yes, and then we have yields of about 2 maize yields, monoculture, 2-3 tons.
Okay.
The residues are removed, so we are only with the roots.
Maybe root also in the future.
So
No cover crops,
basically,
no nothing.
I'm not surprised about it. This is, if you look at the literature, this is what's happening. After 30 years, up to 50% decline in soil organic carbon.
That's otherwise, it looks like we do not need to make any farming, huh? If it goes
No,
like 50% in 30 years, why we need to do farming? Huh? We are damaging our
Was this the
system.
profile, just really quick? I
We are
didn't-
damaging our
20
system.
centimeters.
Twenty
Where
centimeters.
we
Yes.
have most of the cars.
Yeah, right.
So, quick question, for the experiments in Kenya, so this is almost 20 years, 16 years, 18 years. So what we have now done since 2 years, we changed the treatments, in fact, the cropping system. And from monoculture, we are now in systems where we have intercropping with legumes, with brachiaria. And we hope to see now that we get an increase in carbon due to this new cropping system.
You keep very high.
You have a quick question?
Yes, yeah. Thanks, Anton. Really nice study. Want to make any comments about CO2 concentration?
Ah, yeah, it didn't come up much. Yeah, CO2, we're expecting CO2, maybe on the yield very fast. So CO2 concentration increased yield a little bit. And we had scenarios with much more than that. And we didn't see a very big increase. We went to 720 ppm, I think. So yeah, we didn't see a very big effect.
Dealing with the C4.
Yes, it's maize.
It's maize.
Yeah, yeah.
Usually you don't too much see simulation.
Yeah.
There can be a water use efficiency, but.
Mhm.
Okay. I have just one comment. You talk always about climate change, but in fact, you look at factors of associated with climate change. I'm just saying that because the interaction is quite important.
Mhm.
Yeah,
Yeah,
maybe
should
less
be framed.
in temperature and CO2 in maize than in C4, but
Yeah, we didn't look at the interactions.
so it's not scenarios of climate change, it's the factors.
This is the AgMIP protocol that we use.
Yeah. I'm just saying that because we published in AgMIP10 a study on temperature effect. We never use climate change.
We had a lot of
And in the press and so on, they say the wheat yield will decrease by 6% by 1 degree increase in temperature, which is not true. It's not what we said, not with climate change. It was purely temperature effect without taking into account the CO2. Because then we did a study with CO2 and then we showed that it's actually increasing in most area. So just said.
Yeah.
Thank you. So, and the next one. So, said as an introduction, Pierre, I'm a crop physiologist and working at INRAE in Montpellier. And we are working within AgMIP, but also within an international initiative called MI, or Agricultural Model Exchange Initiative, where we developed a framework to exchange modules or components of crop models. And one case study we recently did was on soil temperature models. So it's why I ended up here. So first to introduce a bit about the crop modeling. Nowadays, most of the crop models or crop modeling platforms have some levels of modularities. Could be that all crops share the same soil or same management and infrastructure, or And some of them are also some modularities, level of modularity at the level of a crop or the model system, where each different processes will be developed, simulated, and with independent component that could be plugged together to create a modeling solution, a crop model. So it has been showed many times that that having a more modular representation of a crop and the soil crop system increase the transparency of complex model and facilitate the maintenance of the code, and also it extend the life of a model and its utility. It's also facilitate model intercomparison at the process level, because then you can really compare the model processes, not the full model. It's what I would show here for soil temperature. And that can then, we think, increase the rate of improvement of a model and having less compensation of errors between different components. If one thing that is important is that then you can, if your input and output of your component are measurable, then you can calibrate your model at the level of a component, not the full model. And lastly, it facilitates the integration of components from different groups, and so you can increase the scope of a model and utility of a crop model by bringing knowledge and components from different models, and that's also increased the responsiveness to stakeholders' need to new needs. And if another model is simulating the impact of ozone, for example, not yours, and then you can bring maybe a component of impact of ozone. So this is not a new question, really. Heaps of papers in the literature since the last 30 years at least on modularities in crop models and agricultural models. And how it has been done quite often is to have the modular look at the modularity inside one model, but not between the model. And then a problem that has arisen is that if you want to share components between the model, you will need to develop some ways of exchanging these models. And then if you want to exchange models between several models, then you end up having to maintain and develop wrappers or other ways of communicating and sharing the components. So what we have done in MI is to propose a centralized representation of a component that we call crop2ML for crop meta modeling language. That is a common and shared representation of a model that we can then transform into platform-specific components. So we propose a centralized framework with a unique and standardized model representation of the model. And we don't impose any form of a modularity. So the interface of the components are not standardized. Each model could have its own interface, input, output. And it's transparent in what we wanted is really to have transparency. So we didn't want to share compiled code binaries. We wanted to share source code and in the native language of the platform. So for that, we had to overcome the language barrier, and we did that by a bidirectional source code transformation. And also we wanted a system that conformed to FAIR principles. So currently the system is handling these different platforms of Bioma, DSAT, Conalea, Simplace, Cirrus Quality Sticks, Monica, and AppSim. These are the models that with which we can exchange in both directions, from crop2ML to a platform and from platform to crop2ML models. So we have a generic way of representing the model, and the key aspect was to separate the specification of the models in terms of input, output, parameters from the algorithms. And the algorithms are represented in a language that is Cython, from which we will transform the language. And then each model unit can be composed as a scientific workflow to compose an articulated component. And so, as I said, each model unit with specification and algorithms are transformed into different languages in both directions, from platform to crop to ML and from crop to ML to platforms. So we have developed a number of tools to work with crop to ML. First one is a Python library that allows to create the components and manage them, their life cycle. And also we implemented it as a graphical visual interface in Jupyter Lab. So you can do pretty much the same thing as the crop to ML library, but without programming much. We also wanted to have the model to be findable. So we developed a model repository where anyone can upload a model, and it gives more visibility, and it's a form of documentation of the models, because you have access for all model units, or to the inputs, outputs, parameters, and here you can see the code in different source code, and also in different code for ready for different platforms with the specificity of the platforms. So we did a case study on soil temperature. Why we choose that? Because of the importance of the soil temperature that's driving different processes, both in the plant and in the soil, that are important in terms of adaptation to climate change and extreme weather events. And also it's an aspect that hasn't been compared really a lot between the model. We don't really know what type of error the model makes in terms of predicting the soil temperature. Also, it's driving especially the mineralization of nitrogen in the soil, for example. It's very sensitive to temperature. So our goal was to use soil temperature models to show that components of crop model can be exchanged from across different platforms automatically without recording, thanks to the crop to ML capability of code transformation. And we compared and analyzed the uncertainty of the soil profile temperature in different climates, and to look at also the impact of the error uncertainty of the soil temperature on different processes like mineralization, for example, root growth. And with the final goal is to enhance the soil temperature simulation in crop growth model. So we in the 9 soil temperature models were part of these studies, and we created a crop to ML component for each of these soil temperature models, and we implemented them in 7 different modeling platforms that are here. So, for example, in AppSim, we integrated these 9 soil temperature models that we can now all of them run them in AppSim and DSAT and so on. So first thing we did, and that's the result I will present today very briefly, is a sensitivity analysis of our models. We looked at all the drivers, all the inputs of our soil temperature models, and we did a factorial sensitivity analysis where we consider 4 different soil types, 5 levels of water content of the soil, 3 leaf area index, so 0, so a bare soil, an open canopy, and a closed canopy with a leaf area index of 7. And we use 30 years of weather data that we got from NASA Power for 7 climate sites globally. And we did a continuous simulation for the 30 years. And at first, for this sensitivity analysis, the soil temperature model were not integrated into a crop model. They were run within the platform, but outside the crop model, so without any influence. So, for example, the evapotranspiration was an input of this model, was not calculated by each platform. So we use DSAT to get a realistic soil evaporation and plant evapotranspiration and soil water content over time. But all of them use this as inputs. So we have no confounding effect. So first, we wanted to compare to check that the models, once transformed into in different language and integrated into a platform, gives the same results. And we wanted to check also that if we bring back the model into the original platform, it gives the same result. So it's what is shown here. That's the frequency of data with a precision or an error compared with the original. Sorry, it's very slow. Compared with the original model. And you can see that the precision is always greater than 2 decimal places for all the models. Only for DSAT, we have some simulation where the precision is only 3 decimal places, which we think is quite acceptable for soil temperature. But in most cases, the precision was about 5 decimals. And there will be many explanations for this type of numerical errors. So here's some results of the preliminary result of the sensitivity analysis of the different soils. So here you have the difference between the air and soil temperature, so that we don't have the main effect, otherwise will be the site effect. So you have here the different rows correspond to the 7 different locations. And you have results for, sorry, I made a mistake here. On the left is a bare soil, and on the right, it's a closed canopy, infrared index of 7. And you see with the soil water deficit from 100% a dry soil up to field capacity. And you see that the seasonality of the soil difference between air and soil temperature for the different models. So each color represents a different soil temperature model. So you see quite a large variations between the site, of course. Like if you are in Colombia, in Cali, you see not much seasonality in the soil temperature, and the model more or less agree. But if you go to Quebec, for example, city in Canada, where there's a very large seasonality in the temperature, you see that the difference between the air and the soil temperature, according to some model, could be as large as 20 degrees. But for some other model, it's only a couple of degrees or 0 degree. So there's a large also uncertainty between the different models. And that's for the temperature at 40 centimeter. Sorry, and we also looked at how the model simulates the soil temperature at depth, at different depths in the soil, and you see that also here very large differences between the models. So there's 2 models that don't really simulate the difference. Sorry, I made another mistake here. The second one from the right is sticks actually. So sticks and zeros quality, they don't really simulate difference in temperature with depth compared with other models. Like for example, the DSAT EPIC model, there's dumping depth temperature where the temperature is constant, that is quite shallow compared with other model like the APSIN combo, where you have constant temperature at 2 meters compared with here 60 centimeters. So there's a very large difference in the soil profile temperature between the model. So what we want to see now is to see how what's the error of a model. If there's some model are better than others and to simulate the difference in soil temperature. So the first data set we used is a 9 years follow in Ames, Iowa, in the US, where we have continuous measurement of soil temperature for 9 years. And so we did the simulation with the different models. And again, you can see quite large differences in soil temperature. And then at the moment, we are simulating other data set now with the wheat crop, with different type of environments. So in Maricopa, Arizona, we phase experiments with 2 years in different CO2, water, and nitrogen treatment. And in Bushland, Texas, where there's a 6 years lysimeter experiment that was recently used in AgMIP10 studies. And also in Avignon, France, which was also part of this ET study in AgMIP. So they have good evapotranspiration simulations here and soil water content measurements in these experiments, but also soil temperature, which we will use. And so we want to look at the propagation of error of soil temperature to mineralization and yield. And lastly, we want to do some model improvements. At the moment, in another session, Bruce Kimball is presenting some work he has done recently in DSAT, trying to improve the soil temperature, especially considering the effect of bulk density and water content on the thermal conductivity in the sea. So I'm really blowing up the. So to conclude, we show that the crop2ml can facilitate the exchange of components of biophysical processes here for soil temperature between modeling platform. That soil temperature models give similar results in different languages and modeling framework when we exchange the model between the platforms. And the main challenge really was not about transforming the model and going from one language to the other one. Where we spend most time was really on mapping the input data. That's really where we had the most difficulties, and we had to exchange between the modelers, even though these inputs are relatively simple, but yet it was really tricky. I mean, it took us time before the models gave us some result. So we really need to do something here and to try to refer to a standardized reference of list of variables like ICASA, and to automatize the creation of wrappers. We show that soil temperature models show large uncertainty, and now we're really keen to see what's the effect of this error of the models that can be apparently very large on processes that drive yield variations. So that's the ongoing work we're doing. So the crop2ml is an open initiative. Everything is all the code is publicly available on GitHub, and the model repository is also open. And you can contact us if you are interested. And Cyril Miningoi is here. He's the person who developed crop2ml during this PhD. So if you have technical questions, you can ask him. Thank you. So sorry, it's not good to share session and keep the time at the same time. Yeah, your question.
Yeah. Is it a problem to handle the horizons in soil? I mean, different models have cut the soil at different depths, and you have to be able to exchange between the different ways of representing the different soil layers. Is that a problem?
No, most models you can choose you can adapt the thickness of the layers. So here we use the 5 centimeters layer, I think, Cyril, the 5 centimeters. So for most all models, you can do, for example, sticks, they simulate with 1 centimeter. So what we did, we took the average of the 5 centimeters.
Okay, you fix the depths in the module, and every model adapts to that.
Yeah. Usually in the module, you can define that. Okay, so next speaker. The time here if you want to.
Good afternoon, everyone. My name is Maria Lisa Pocinelli. I'm a PhD student at McGill University and working in collaboration with Agriculture and AgriFood Canada. And I'm just going to be presenting some preliminary work we've done on calibrating the sticks crop model for a new potato cultivar in Atlantic Canada. So the new cultivar is Mountain Gem Russet. It's becoming increasingly popular in Prince Edward Island. Prince Edward Island is Canada's smallest province, but also our third largest potato producer. And Mountain Gem is now outpacing Russet Burbank in terms of hectares planted, which is pretty big, as Russet Burbank is the most popular potato cultivar to grow in North America. Mountain Gem has good disease resistance, and it's reported to have 15% higher yields than Russet Burbank, as well as 13% less nitrogen input needs, which is why it's becoming so popular. So our objectives were to calibrate and evaluate the sticks crop model on plant biomass and tuber biomass and uptake, LAI, and cumulative N2O emissions, as well as to determine some crop-specific emission factors. So our data set consisted of observations collected over the growing season of 2024. It was rain-fed and a bit of a dry year last year, but we have 2 nitrogen input levels, as well as 3 typical crop rotations for potatoes and PI, with 3 replications each for a total of 18 subplots. And for the purposes of calibration, we split these in half to have 1 as the calibration set and 1 as the evaluation set. So Styx was chosen because we already had it well calibrated and evaluated for Russet Burbank in Eastern Canada, in Quebec, and Atlantic Canada in New Brunswick, as well as for the Shepherdie cultivar in Prince Edward Island. So one of the things this calibration brought up to us was really highlighting some of the steps we needed to take into account for potatoes' unique growing conditions. So after sowing, around 20 days after sowing, when the plant is about 20 or 10 centimeters high, we hill the potatoes to about 30 centimeters. And we noticed that in our initial runs that our soil moisture simulations were quite a bit higher than our observations. And when looking at the difference between our measurements in those hills and the furrows, we found that the hills were about 75% soil moisture of the furrows. So we adjusted our field capacity and wilting point by that factor to lower the simulations, which did improve the simulations in the range of our observations, but they're still, as you can see on the right, a little bit high. So for calibration, we made use of the optimization algorithm provided by the Styx model. We started with parameters that are involved with emergence and starting, moving on to leaf development, shoot and root biomass growth, nitrogen uptake, and then yield formation parameters. Styx also has cultivar-specific parameters, so those were calibrated separately in a similar order to that listed above. And finally, we calibrated for our cumulative N2O emissions. The main statistical criteria we were looking at was the root mean squared error, systematic and unsystematic, where the systematic error gives us an idea of the error in the model due to bias, and the unsystematic error gives us an idea of the error in the model due to data dispersion or the precision of the simulations. And so based on some of the results, we generally had good satisfactory simulations for most of our parameters in our calibration. One thing I will point out also that this calibration brought to light for us was that the Styx crop model does not have parameterization currently for tubers to be modeled separately than the above ground plant matter, except for sugar beet. So in our case, we had to combine our measurements and picture the potato tubers growing on the plants like fruit. So that is how our total biomass observations are put together. For our evaluation, most of the parameters remained in a satisfactory range, although LAI and root biomass did become unsatisfactory, and our tuber nitrogen was just right on the edge of our satisfactory range. We also had some additional observations that the model wasn't explicitly calibrated for. Again, majority in our calibration were satisfactory except for root nitrogen. And in our evaluation, root nitrogen and root carbon were in the unsatisfactory range, but yield and total fresh above ground biomass, including the tubers, was in the satisfactory range. A lot of our parameters are above that 1-to-1 line, which indicates that a lot of the model error was due to bias, which leads us to believe that we do need to improve the parameterization of these variables. And we did see a lot of them being under-predicted. So while they were well simulated in terms of the precision, they were quite a bit below our observed values for a lot of the parameters. So just looking over our cumulative N2O estimations. So these were calculated based on flux measurements that were taken between May to October. These were then converted to daily nitrogen rates, and the cumulative estimations were calculated through trapezoidal interpolation. We did also include some simulated daily values from sticks in our cumulative estimations to take into account that cumulative N2O emissions that we didn't have daily observations for. And in general, it was under predicted. You can see in the above plots, which is our high nitrogen rate, very much under predicted. It was somewhat well predicted for the lower nitrogen rate, but as you can see in the middle, still a little bit under predicted for even our lower nitrogen rate. When looking at emission factors, the IPCC recommended emission factors for Canada range from like 1% as a general value to 1.2% for Eastern Canada and 1.6% for a humid environment. Looking at our simulated values, they're well below the IPCC emission factors. As previously said, due to the fact that our cumulative N2O emissions were underestimated, especially in the higher nitrogen rate, we do get very low emission factors from our simulations. But from our observed measurements, the higher nitrogen rate shows higher emission factors than what the IPCC recommends for Eastern Canada. And for our lower nitrogen rate, they are around the range of the general emission factor given. So another thing here is that these are based on our measurements from the hills alone, and we're missing a whole other half of the field from the furrows. And the measurements between the hills and the furrows could vary quite wildly, but we're unable to simulate those dynamics with the sticks crop model. So that's one of the additional factors that we'll need to look at in order to improve our cumulative N2O emissions. So in summary, this preliminary calibration really brought up a lot of the considerations that we need to take for potatoes' unique growing conditions. In general, our model had satisfactory performance for the root mean square error, systematic and unsystematic, but our root parameters and our LAI were poor in our evaluation set. And the model error was generally due to bias, indicating that we do need to improve our model parameterization. So our next steps are to improve our cumulative N2O and soil moisture simulations, especially with those higher nitrogen rates. And this will involve incorporating an additional year of data at least, and also incorporating and simulating those cumulative N2O emission contributions from the furrows. And as well, we hope to evaluate these impacts by applying this to conventional farms at the field scale as well. Thank you very much. And yeah, I'd love to hear your thoughts or comments.
Okay. Question in the room or online as well, if you're
So thank you for your presentation. I must say, I don't know the module of N2O emission in sticks, but do you know why you underestimate the N2O emission with sticks? Is that because of not well simulating the temperature and the moisture, or is it because of the module itself that is?
So it's a really good question. Thank you. I haven't looked into it too much in depth, but I do think it involves the simulation of the soil moisture. When we did have it as a higher field capacity and a higher wilting point, we did get better simulations for our cumulative N2O emissions. So there is some discrepancy there. We could keep them higher, but at the same time, we want to well simulate that soil moisture in the top 15 centimeters of the hills.
So that means that the module itself is doing well. If you get the moisture, okay, then.
I think so.
Yes.
That's what I think. Yes.
Yeah. Well, the moisture was still over simulated, so I
Yes.
actually don't think that would be it.
Okay.
However, you can parameterize sticks for N2O to increase that N2O emission. I mean, I'm a DNDC and DaySet monitor, but we work strongly with Jigo, Guillaume Jigo.
Yes.
You might know, but he can demonstrate how to parameterize it.
Yes, I did get some input from you. Yeah, I did. And we are looking, I think I would play it a little bit safe when parameterizing some of the N2O parameters, but we definitely have some more room where we can play.
I'll just add that we're running DNDC DaySet sticks and DSAT against long-term data sets, 22 years, one of them of continuous measurements. And sticks does really well across this 22 years in the growing season and the non-growing season. The only period it doesn't do well is spring thaw because it doesn't have a special spring thaw emission component. And that's absolutely required if you want to simulate that spring thaw emission.
Mm-hmm.
Yeah.
Yeah. Can you go in your moisture data? Because what I was also noticing is your moisture is very low, 18.5% fill capacity. It means this soil is sandy soil?
It is, yes.
Very much sandy. It should be 90% or 92% sand.
Maybe not 92% sand, but the dynamics of the hills can be quite different because they are about 30 centimeters high compared to the furrow. So there's a little bit more surface area there as well. And if anyone has any comments on this, I would love to hear that too. As well, these were measurements taken just at a certain point in the day. And so I do have to wonder if there might be more variation if we did have an average soil moisture for the day. But these are the measurements that were collected.
Anyway, probably this should be very much sandy soil, otherwise 18% FC is very low.
It is quite sandy.
And if you increase the FC level, then your model can somehow this measured value and simulate also maybe you can do that one. Yeah, verify. That's good.
Okay, you did very well in time-wise, so you can have another question. You have a question about parameterization, I'm sure.
No? Actually, no.
Oh, I'm disappointed.
I have a lot of questions about parameterization, but I won't ask them. You did data splitting to evaluate how well your model works.
Yes.
And it's okay, but all of this at one site.
Yes.
And that is extremely dangerous because you don't really know how well the model is going to predict for other sites. Is there any way to get data from a different site?
That might be tough for us. We do want data from different years, but I will say it might be difficult for us to get it from different sites.
Because the problem is that you adapt the model specifically, partially the parameters that you estimate are adapting the model to that specific site.
Yes.
So it works better at that site, but when you apply it to a different site, you don't know what's going to happen.
Yes. Yes.
We have data for probably 50 sites in Canada, but not much for potatoes.
Okay, yes.
Lots of other crops.
Yes, I think that because this is our first, last year was our first time collecting data for Mountain Gem. I have different sites for Russet Burbank, but I'm unsure if we'll be able to do a completely different site for Mountain Gem. Ideally, we would have to see if that's possible for my lab to do. So.
Okay, thank you very much.
Thank you so much.
Thank you.
Can I share my screen?
Yes, sure. No, you're a speaker? You're the next one. No?
Not sure.
So at 6, but then you called up. Yeah.
Okay.
You did have it 6 before, but then.
So this one is before?
Yeah.
Yeah.
I think you had that. Yeah, in the list you had it.
Okay.
And this.
Okay, doesn't matter. Okay, so you can share your screen, of course, yeah.
Okay. Is it? Can I see the screen?
Yeah, perfect. Thank you.
Okay, thank you. Thank you for the opportunity. I would like to share today about new AgMIP RISE team activity about estimating methane emissions and greenhouse gas mitigation. I'm Toshi Hasegawa, Naro in Japan. I'm leading AgMIP rice team. I have to apologize, there are no results yet, as it's really a starting point of this new activity I'd like to share today. Okay, so brief background, as you know, the rice is mostly grown in Asia, but it's now expanding to Africa and South America as its nutritional value of this important crop. Agriculture contributes to about 20% of greenhouse gas emissions, with majorly land use change playing a significant role. And rice cultivation, as you know, is one of the major sources of methane that's responsible for about 6 to 11% of anthropogenic methane emissions. All these methane emissions from rice paddies is very complex that is affected by climate and soil types, water and organic matter management, rice varieties, and agronomic practices. And understanding these factors is crucial for climate soil plant interactions and effective mitigation strategies. So there are methods of estimating methane, including some of the very empirical models like IPCC Tier 1 method or Tier 2 method, or some of the process models like Tier 3 methods. Here's one example that I borrow from Nicolaisen et al. That shows this measured methane emission on the x-axis versus estimated daily methane emissions over the season. As you can see, there are different methods, and that's mostly the measurements vary widely than the estimates, and that means some limitation of current method models. And this process models, but a comparative evaluation across models is still lacking. And there are some consistencies in current estimation approaches. So addressing these gaps is essential for improving greenhouse gas emissions mitigation strategy in agriculture, particularly rice agriculture. From the previous AgMIP rice activity is as follows. We did mostly started with the very lightweight and maize. We started from uncertainty evaluation, crop yield, and growth and yield at 4 different sites. And we also did some interesting model classification of different rice models. And we also tested our rices in terms of CO2 responses using phase and chamber experiments. And some of the temperature responses from chamber experiments are tested against the most crop models that failed to show the very extreme events of heat. And some of the G by E interactions are also our main project and trait-based model ensemble for rice plant type design and genomic and crop modeling for prediction of rice days flowering, phenology in terms for all the integrated phenology with genotypes. An ongoing challenge still exists about G by E interactions in multi-location yield trials, but our focus has been mainly on plant responses to environments, not much so on soil. So our new challenge is this, including rice growth and the methane emission of the using carbon metabolisms. As you know, the methane, soil carbon is either oxidized or reduced to methane under whether this aerobic or anaerobic conditions. And this process is highly influenced by plant existence. Without rice, much less carbon input into the soil. As a result, less emission from methane emission. And rice itself also influences methane diffusion from the soil to the atmosphere. The methane transport is a complex process, including bubbles and also the plant-mediated transport. But these are the very sensitive interactions among the rice field. So our new challenges here, we want to do some multimodal approaches for CO2, methane emissions estimation from the paddy field. Our primary objectives is assess the capability of current rice models to simulate methane emissions, rice growth and yield under varying soil, water, and climatic conditions. Our goal is to quantify the methane reduction potential of key technology across different climates and environmental conditions. as many as 16 rice models have been involved in AgMIP rice activities, but not all models are capable of simulating soil processes, including methane emission. The models with the red letters are the ones that can simulate methane emissions. So we can't involve all the rice models in these activities, but I think a subset of models, still 1, 2, 3, 4, 5, 6 models that can be involved in this new challenge and for methane emission estimation. So the potential data sets are still limited, but I think we needed really more data sets. But I think that we have already obtained some high quality data sets at 3 different sites in the world, 2 from Asia, 1 from South America. 2 from Asia are from the phase experiments, 1 from the Shizukushi phase experiment in Japan. The other one is Wuxi phase in China. These 2 have multiple years, at least 3 to 5 years of experiments, and with different CO2 levels, nitrogen levels, in some cases in temperature treatments. And other sites is from Brazil, the Capão do Leão, that had a different water management regime, including AWD. AWD, perhaps you are well aware, is alternate wet and dry irrigation that originally aims to save some water, but it's also becoming increasingly important in terms of reducing methane emissions. We have all the crop data, multiple year of treatments, and crop soil properties, management practices, daily weather and seasonal methane emissions, high frequency methane emission measurements. So I think these are one of the very high quality data sets that can be initially used as the this protocol. The protocol is still a developing stage, but I think I would like to have your good opinion about this. We're trying to have a very similarly to the other many major activities. We want to have this 3 stages for the comparison. The first one is always start from the blind stage, but the blind stage in this case is limited to the methane data. So modelers will be will given the basic crop data from 1 experimental data set per site, but without any measurements of methane. And they will run the simulation of full sets of experimental treatments for all different years. And this stage will try to assess the baseline performance of models in simulated methane without any specific tuning for soil or methane measurements. They will go into the second stage of the calibration stage with the partial data. Modelers will receive CO2 emission data for only 1 data set per site for methane emissions, and they will be allowed to refine the models using this limited data. And at this stage, we aim to evaluate improvements in CO2 methane emission simulation accuracy after partial calibration. And finally, we use the calibration with the full data sets. Modelers were given full data sets and have chances to further tune their models. And this final version will be used for the further sensitivity analysis. So the analysis is planned like this. The basic baseline uncertainty is a blind stage, compare models outputs against experimental data to assess the spread of prediction before any tuning. Quantify inter-model variability of the metrics such as standard deviation, confidence intervals, and ensemble range, and evaluate bias and systematic errors across models. And we try to go on to the reduction in uncertainty. Hopefully, we can reduce the uncertainty using calibration with the partial data to analyze how to access the limited efficiency of the methane emission data that reduce the uncertainty. And they compare the variance prediction before and after calibration, assess whether the model's coverage would observe CH4 emission after partial calibration. And followed by the scenario-based sensitivity analysis in fully calibrated models. The model will respond to different climate conditions, soil property, and management, particularly water, is one issue. The other one is for the organic matter management. and also are interested in the different input data such as temperature and CO2. We already know that temperature and CO2 have tremendous effects on CO methane emissions that can have a really strong feedback effects on climate change. So we hope that models are capable of doing this. But additionally, we are still searching for additional data. And fully calibrated models can be tested against these independent data sets. That's still ongoing. We know that there are so many methane emission data available in mainly Asia, but we're trying to have the really high quality data that can allow us to have the high quality simulation. So their protocol is still tentative. So we welcome your comments and suggestions. We are still, like many others, we're seeking for additional data sets. Collaboration from the experiment is highly appreciated. We're planning to have on, I think it's on Friday, we have a RISE AgMIP team and also Global Methane have a discussion during the AgMIP RISE, during the AgMIP10. And also, we are planning to have one meeting, physical meeting in the Philippines in August and September, with possibly with the potential experimenters. So we try to implement this with the more involvement with the people. Thank you very much for your kind attention.
Thank you. So, questions, comments on the protocol? Yeah.
Sorry, Tim. Went through. I think this is great, Toshi. It's Sonali McDermott here. And this dovetails nicely with some of the MACV, the mitigation adaptation co-benefits work that's all RISE focused at the moment. I'll talk a little bit about that on Thursday. I guess one of the things I was thinking about is that for the MACV work, we coupled, well, Tau coupled ERISA to DNDC. And in light of your modularity discussion, I wonder if a topic like looking at yields, because you're going to be calibrating the yield, you're calibrating and evaluating the methane, Toshi, but I guess I'm assuming you'll also have to do that for yields. So now you're dealing with like a multi-variable calibration where both kind of have to align, which is not something we've done a lot of before. And then there's multiple factors across, the variety, the environment, the management that have to be tested for sensitivity wise. And I guess I'm just wondering about the intersection of all of this work with something like it would be really great to use a RISE or use a RISE module, yield module against a whole bunch of soil modules and kind of see what that looks like. So that's just a comment about where modularity comes into this, because that's how Tau kind of uses to begin with. And then the other part of this is with the single factor and multi-factor, looking at not just CTWN separately or irrigation separately, but looking at the multi-factor interactive effects of the factors C3MP style or something might be worthwhile doing because those seem to have an effect in the work that we've done so far. So just a couple comments there.
Thanks very much. It's all very relevant and it's really challenging as well. At least, as you said, right, we have to calibrate with the crop yield, growth and yield, and that's the must thing. And we have to do that in the beginning. If that tuning into the methane would change that the responses of crops and yield, and that's also another very, very important issue. So we haven't been able to tackle that yet, but I think we have a really close eyes on what the tuning of the soil part can have influence the crop part as well. So that's really I'm really excited to see how that goes. We don't have a really clear idea of how each modeler will tune themselves into this multiple complex situations, but I will see how they go. We'll go with that. We will have to be transparent in that aspect as well, so we'll to know how it goes. And also, this additional sensitivity analysis involves a lot of different factors, and I think it's really immensely important, particularly in terms of water management. And they can save water, but at the same time, there's some penalty on the yield. That's really crucial to simulate very well. Otherwise, it's no farmers will adopt this technology. So that's also an immensely important part. Thanks very much for your very nice comments.
Okay, thank you. I'm sorry, we are really late. We move. No, we are just we are half an hour behind. Thank you very much.
Thank you.
Yeah, thank you. If you can, yeah, stop the sharing of your screen,
Yeah,
please.
Yes.
Thank you.
Okay.
Okay, thanks a lot. Okay.
Okay. All right, thanks. Well, yeah, thank you for joining, staying around a little after the session was posted. This is fairly different than all the other talks. We're making use of some of the soil simulations, for instance, but this is really this is work. I'm a senior agricultural economist at Research Triangle Institute based in North Carolina. And this is work with EPA. It's like the fourth round of these updates of like global assessments of non-CO2 greenhouse gas mitigation potential. It just got released in January 2025, like right before the inauguration. And so like the prior ones were in 2006, 2013, and 2019. So this one just came out. So some of these data have been used in other economic models and the image model and GloBiome and others to try to, as sort of an input to then look at competitiveness across different sectors. But so, as you all know, largest source of non-CO2 greenhouse gas emissions is agriculture, and they're expected to still continue growing rapidly. And a lot of the assessments, if you're looking at mid-century or later, agriculture tends to become like a bigger and bigger share of what's left under these net zero scenarios because it's some of the more difficult emissions to get rid of. And so, the studies have looked at a lot of mitigation options before. Generally, it's, with some challenges to really getting the emissions out of the ag sector, even compared to other sectors. But so this is a new set of this global marginal abatement cost curve data set. So it's bringing in some economics estimates of costs as well. Where there's some updates, just new opportunities covered for livestock, which no one else has talked about in this session, but we use descent simulations this time for rice. We'd use DNDC in the past. But as part of this new EPA study, they switched over, and it does, as sort of the previous speaker referenced, the whole pattern of emissions actually looks fairly different. You have more methane, less N2O. The yield effects are a little bit different. And descent and DNDC, maybe not totally surprising, and just generally updates across all of the sectors that were modeled. Again, one of the things is just, again, for those of you, the people in this room, maybe less than some, like the global econ teams. I think Maxim's maybe familiar with it. I don't know about a lot of the others, but it is up on the website, again, somewhat quietly. It came out like, it was meant to have like a whole report with it, but it had to get rushed out, and the data is there. There's not like a whole accompanying report with detail yet. Hopefully there will be eventually. Again, there's lots and lots of challenges doing this. There's certainly lots of uncertainties that are somewhat smoothed over, trying to characterize like average potential at this level, again, to give a sense of what the mitigation potential might look like, and relative costs across different options. Again, some of the ways we're trying to at least partially address some of those challenges is we are using global gridded outputs to try to characterize spatial and temporal heterogeneity, and looking at 5-year time steps and some of the dynamics over time, non-linear responses, and capturing the multi-gas interactions to try to look at net greenhouse gas impacts of all of these options. And then the grid is being mapped out to approximate at least 195 countries is what the data set covers, going out to 2080. Basically combining biophysical modeling with estimates of associated changes in costs and revenue to get at net changes in cost, or basically trying to work up to like what is the the break-even cost, or what's the net like incentive you would need to break even if you changed and and adopted a given option that's going to affect your yield, it's going to affect your input use, it's going to affect other costs of production. Although you may also get a co-product if you have a if you're able to sell energy from a livestock project, anaerobic digester or something, so you may get revenue out of it as well. And so trying to look at what the relative costs are, and then marginal abatement cost curves, if you're not familiar with them, are basically just ordering all these individual options from least to most expensive to look at where are the relatively lower cost options. Again, I'm not going to spend too much time on it, but just it's the break-even prices, again, just looking at accounting for the cost, the changes in all the costs going in, all those input costs, changes in revenues, due to changes in yields of the product, as well as potentially co-products, and looking at, okay, how much of what's the net cost, kind of the minimum incentive. I mean, in reality, it's probably even higher than that to overcome barriers, riskiness of changing other things. But this is just the break-even cost. Again, some of the main changes in this new version, extending through 2080, using some projections of agricultural activity. So it's using like projected changes in areas and baseline yields and other underlying representation of the global ag sector, as well as projections of changes in baseline nitrogen fertilizer use that went into the DayCent model as well. And generally updating data from more recent literature. Some of the ones I'll just briefly talk about, given there's not a lot of time for these presentations, but there's also an effort to regionalize some of the major crop varieties in DayCent, expand DayCent coverage to capture more crops and to capture grasslands for the first time, for us at least, to have grasslands and look at like net impacts associated with improving forage productivity that is going to, at least ideally in a lot of cases, improves the efficiency of producing livestock products. Although there may be more N2O emissions from, depending what you're doing, if you're adding fertilizer or you're doing something else, depending what you're doing to the grasslands. And then new livestock technologies. Again, so in terms of regionalization, this time in the past, DayCent was looking at like basically a single global variety that they were growing everywhere. This time there was an effort to regionalize and look at, this is an example for maize. The major crops were regionalized this way. Looking at maize, like where all the areas where they had data on maize, and then separating them out, basically trying to capture differences in genetics and differences in the specification of maize by region, so you could better match up to yields. Because in the past, you would find that like some of the regions just not surprisingly, didn't match up that well, weren't that well calibrated. So trying to better calibrate to specific regions. And also in the past, there were only a few major crops that were simulated, and this time they're not regionalized, but they also simulated cotton and hay and sugar beets and sunflowers and a lot of other crops that hadn't been done in the past, to try to give a better coverage of the fertilizer that's being used and where these N2O emissions are coming from, and what might happen then under changes in practices to mitigate those emissions. We also used DayCent to model rice cultivation this time, which was largely like EPA wanted to be more consistent, maybe some practical reasons for doing it, although it definitely, it results in differences in what the outcomes look like, switching the models. And also, again, looked at grasslands for the first time for this effort, this global mitigation study. So for livestock, for instance, for this, there was addition of some feed additives which had, that are promising and get a lot of attention. Although there still are some barriers practically. There's still, a couple of years ago, I think, John Kerry and others told me, this is going to like wipe out all the emissions from livestock. But in practice, I mean, because there are experiments showing like 85% reduction sometimes, and really, really high reductions compared to a lot of livestock mitigation. If you're familiar with it, is often really low. Like you're doing something that's getting like 10% or 5%. And it's really hard to get rid of some of these like enteric fermentation emissions, but looks promising, but there are, still like you have to keep feeding the animals the additives all the time. Like you can't just give it to them like once. And, if they're not eating it, then they just start emitting methane again. So it's a real challenge with grazing systems, issues like that. Other issues with some of the red algae is considered an invasive species in a lot of areas, and there's potential human health concerns and animal health concerns. So there's still things going on with that, but it was incorporated with some assumptions around how it may evolve. Like basically every ag company is doing research into this and trying to work on extended release or other ways to basically make it more applicable to more systems. And also added some options that have been a lot of interest in the US, partly because of policy drivers, but for renewable natural gas produced from biogas, where basically you're upgrading it to a quality you can put it straight into a natural gas pipeline. But it's capital intensive. I mean, a lot of that's being driven by, you can get credits out of the California market and from the renewable fuel standard in the US for doing it. So almost all of it goes into transportation markets because of the policy incentives. But so, looking at that as a potential option. Yeah, again, just briefly, this is like just a global, I mean, these are, again, they're generated for other years at a country level. In the US, it's broken out the state level. We're working on breaking down a couple other countries further too. This is just a global aggregate, all cropland options combined. What is that marginal, what does that marginal abatement cost curve look like? And this is just showing like how much is the dark blue is an estimate of how much, at least based on this, is potentially reduced at like a less than zero cost. At least implies that like now as an economist, you always wonder like what's going on or what are you missing? What are the other barriers? But at least implies that, the yield improvements are greater than the cost based on what's going into it. And the light blue is where you can get additional mitigation, but at some, you need some incentive to do it. And then the 71.8% that's still left is more like there's no technical option that we have, at least right now in this model, that would get you that much of a mitigation. Because a lot of the options, again, running them through data science just don't get you that much of a reduction. And just looking at, 2030 to 2050, it's pretty consistent. The baseline emissions are still rising based on available projections. Again, just overall characterizing what it looks like. Doing the regionalization led to improved matching of yields. Baseline emissions, unfortunately for the planet, look, assuming that's right, look worse than before in terms of like where have we gotten since the last time we'd done this in the 2019 report and more recent projections. Reduction potential is also bigger than before, partly because again, we have this a better coverage. We're covering more crops. We brought in grassland, so part of it is just more complete coverage. Similarly for rice cultivation, there are methane emissions from, according to the dataset model, are considerably higher than they were from DNDC. Nitrous oxide emissions are lower. They also had opposite signs on like baseline, like net soil carbon change. Sure. And, similarly for livestock, again, baseline emissions are actually growing faster than they were last time. I mean, emissions have continued to grow fairly rapidly on some of the methane sources in particular. A lot of this depends on assumptions about technology improvement and adoption, but tends to have more potential over time with some of those options coming in. And again, really the main message is just more that there is an update available potentially out there for again, like other ag models have used it, say in the past, to look at, well, how does this kind of high level average, at least, relative cost of different options. If you pull that in and you're competing, say under a climate policy, like, where might you draw mitigation from across countries and sources, et cetera. And that was all. Thank you very much.
Question in the room or online?
Sure. I have a quick question. Thanks for the update. Nice presentation. I did actually also miss the announcement that it was released, so now shouldn't email the colleagues. I was just wondering if you can comment a bit comparing, overall mitigation cost 2019 versus this update. So you mentioned you introduced a number of new kind of features, but at the same time also emissions have increased in the baseline.
Yeah.
I suppose there could be some, compensating factors. I was just wondering, did you notice any, major changes in general in costs, or, they're roughly on margin and it's.
Yeah, no, it's a good question. I mean, it tends to be the changes in costs are smaller than the changes, I think, in the biophysical. Where some of the changes in cost came in. And for instance, in like rice, I think it's a little more expensive than last time. But part of that, or even a lot of it, was probably related really to like the data model having a less positive yield response to some of the changes in water management than the DNDC model did. So then in terms of like, some of the benefit to farmers was potentially like a yield gain, and now the yield gain is smaller. Some of the new options that are in are relatively expensive, like the feed additives. So yeah, I guess the feed additives too, it tends to give you more mitigation potential, but at a relatively higher cost.
Thank you very much. Sure. So the last speaker of the session is online, connected. Yeah, Nathan, if you want to share your screen.
Great. Please let me know. Cool. Can you see and hear me okay?
Yeah, we see full screen and we hear you okay.
Cool, thanks. And I gather that I'm the last thing between you and dinner or beer, so I will be quick as I know we're also over time. So I'll crank through these, but happy to follow up, and thanks for adjusting the schedule. So just to get to it, my name's Nate. I'm going to talk about kind of what I just call rice MRV, tracking, quantifying rice management practices, environmental outcomes. And a big team, really, Ishan has led a lot of this modeling work, so I will give him a lot of that credit. So I think most of you, I don't need to, do a big pitch here. We're going to continue to kind of scale climate smart ag. It's a little bit of a lull for political reasons here in the US, right? But we don't need to get down. We'll keep going. We take what I just call a GeoAI MRV kind of approach, remote sensing, crop models, field data, etc. We kind of put all those together. And really, it's my pitch to AgMIP. There's different companies out there using different tools, different technologies. Some are very sincere, some are very thoughtful, others, not so much. Often you kind of get somebody that gets some code or quote unquote a model. They do some black magic, put some IP on it and claim it's private, and you don't really understand what's happening. So that's going to be challenging to kind of really scale impacts, right? So I would throw it out there. Somebody like AgMIP, an institution, an organization like AgMIP really could help sort of lead a big intercomparison. It was nice to hear Toshi, although don't see him here anymore, but kind of somebody that can standardize all these data, all these models, so the community out there can use the best available science. We want everyone using the best available models, best available science. So there are certain practices that the market is more receptive to. I kind of work in compliance markets and VCM, these ecosystem service markets, part academic, part private. So how can we influence management and monetize those outcomes? So some of these practices include seeding, DSR versus transplanted paddy rice, et cetera, irrigation, AWD versus conventional or continuous flooding. We do a lot of work lately in crop residue management, kind of these burning emissions is kind of a big deal. And then there's all these kind of what I call second level types of potential managements, different practices, and we do different experiments like biochar, methanotropes, et cetera. So these are some of the key levers that as a community, we can pull in landscapes and get farmers to transition, to try different practices. To do that, we have to kind of quantify them, right? We want to track them, measure them, understand. So we want these tools to work across systems, across scales. So we tend to work in places where we have good data to do like a lot of our CalVal exercises. Typically in each agroecological zone, you want to tune and calibrate these different models. So a lot of work in kind of South Asia, India. I'll share a couple of examples from North and South India. Very small fields, very little infrastructure, very little data poor. A field might be 1, 2, 3 hectares in the north, maybe, or sorry, in the south. In the north, maybe it's a little bit bigger, 6, 7, 8 hectares, all the way to something like Arkansas, the mid-south, commercial scale production, 80, 100, 40 hectare fields, lots of infrastructure, flux towers, etc. So we've kind of built up these calibration sites to help tune and test our different technologies because we want the most robust. We want them to work. So I think folks have probably seen similar types of slides or work. These are just kind of some snapshots to give you the idea of some of the chamber data we're collecting. And I'll give some examples from Punjab, India, Northwest India, typically rice wheat rotations. We mostly work in Haryana, Punjab area, kind of near outside Patiala. So again, very tedious work, takes a lot of effort, a lot of time, but cost effective versus someplace like California, Texas, Arkansas, where there's a lot more infrastructure. So here we go out every few days, once a week, depending on the season, logistics. We kind of take these measurements. You want to have them very consistent and detailed SOPs. We have very thoughtful controlled treatment design kind of experiments, in simple terms, field with AWD, field without AWD, only, much more robust and rigorous. And of course, we're measuring methane, nitrous oxide, and as well as water quantity and a suite of other parameters. So pretty thoughtful in-field sampling across these different districts. Kind of more my technical background is on the microwave SAR remote sensing. So this gets into kind of some of the physical retrievals, some of the AI ML workflow. We use strip map quad pole L-band data. L-band are nice long wavelengths, so you can really penetrate the canopy, get into your target scatterers. These are from SOCOM, an Argentina satellite, which gets us essentially an observation every 4 days if you use ascending and descending. So what we do, we have those super sites and those roadside surveys, people in the field during overpasses, and then we run our physical retrievals. And what you want to do from the L-band data is capture those different scattering mechanisms. That lets you kind of derive those physical parameters. So if you, in lay terms, as you can see from the cartoon, what we want to do is track that double bounce signal. That tells you whether or not that paddy is inundated or not inundated. From that, then you can get a better sense of that irrigation practice or the hydro period. How often, how long, how frequent is that paddy flooded versus not flooded? So we do that throughout the growing season, throughout the irrigation season. So we have been working with a few different models, and I am a promoter of open access. So working with Tau and others at Erie on kind of what I just call version 3.5 or 4.0 to be released soon. The model, of course, has different parameterization fields, crop management, soils, weather, etc. So you can imagine we take those remote sensing field scale indicators of irrigation, and then we drive ORISA basically. So what's the irrigation systems? What's happening? A lot of other parameters. I won't get into all the details for the sake of time, but we kind of have IoT devices, biomass, GHG, a lot of management data, etc. So just some quick results. Again, these are from Punjab, outside Patiala. These different treatment control sites. You can see from AWD, conventional flooding, and DSR. AWD and DSR generally have similar biomass and plant structure compared to conventional flooding, so that's good. The management is not hurting yield. Maybe here and there at one site, you could say DSR maybe has a little bit lower grain yield, but I wouldn't say that's universal. Then on the right, you can just see kind of some quick snapshots of some of the methane changes from, I think it's days after transplant. So here you can see in some fields, AWD, multiple orders of magnitude lower methane. DSR, we've seen pretty consistent that if a early and quality dry down happens, that can have season-long implications on both methane and nitrous oxide. So that's kind of interesting to see. So take-home message here, AWD seems to be having a pretty powerful impact on reducing methane. Again, just some quick snapshots, kind of a cartoon of what that looks like over a landscape. You can imagine we get those time series L-band measurements of physical scatterings to look at those irrigations. So basically, how wet or dry is that field, or how long or wet has it been? And here we ran the model with some of that irrigation parameterization. You can see, again, just going kind of quickly, it does an okay job, although you might argue that the prediction for the impact of AWD in Punjab tends to be over predicted. So it's actually much lower, probably because the soils are so terrible, right? The very depleted soils from about 5 decades of overuse. But generally speaking, we're doing a decent job of capturing the GHG emissions using those irrigation parameters from remote sensing. Just a couple other graphs. Again, I don't really have time to go through all these, but the take-home message again is that AWD, much lower footprint of methane. So it's about 65% lower emissions. Now, of course, the truth is in Northwest India, the emissions are very low because that soil is so bad to begin with. Even the baselines are very, very low. But good to see nonetheless. We're able to track that pretty well and quantify it. On the right, you could just see some graphs of N2O with those green areas, those green arrows denoting some of the fertilizer management, some of the nitrogen applications. So nice to see that those are being captured. Slight increases in a couple of the sites of N2O from AWD, although keep in mind, in these systems, methane is by far 90–95% of that GWP. So yes, AWD tended to increase N2O at some sites, but overall, it's still a small fraction. So really quick, and I'll let you all go get your dinner and a beer and have fun. Take-home messages, Arise to 3.5, pretty robust all in all. We do want to see more comparisons, more experiments. AWD and DSR reduced methane by about 50%, 75% respectively. Noted AWD slight increase in N2O, but that, of course, is a fraction of the overall GWP. I would tend to promote using some of those L-band data to track the irrigation. NISAR should be launching hopefully in a month or so. Until then, we have PALSAR, we have SOCOM. And generally speaking, taking the advances in, compute and different deep learning to drive those models, I think is where the community could go over the next 5 or 10 years. I think that'd be really cool, but somebody needs to help set up CalVal sites. Somebody needs to do those intercomparisons. Great if AgMIP and the community could step up and do that. Happy to help, happy to support. And lastly, yeah, happy to collaborate. If anyone has any comments or questions, please reach out. Otherwise, thank you and enjoy your time in Mexico City.
Thank you.
Yeah. I'm Krishna Devkota. I worked for AD for around 7–8 years, 6 years, and in AWD for maybe 7–8 years. For me, you emphasized a little bit overemphasized AWD because this is well known that AWD reduces methane gas. That's well known already. For me, this is not the new news. And you did not show the data set of N2 and other leaching things because in AWD, leaching always is more, and similarly, the nitrous oxide emission is also high. And in your graph, you have significantly lower yield of AWD compared to conventional flood irrigated rice. And you also said this is slightly, but this is when I see your graph, this significant figure is there. So I think, and there is all the time big challenge of wheat pressure in AWD. How you justify and how you bring all those things and make the recommendation which can be valid now. Yeah.
Thank you. Yeah, I didn't quite get 100% of that, but happy to follow up, happy to talk. Really what we do is for every single field, we optimize what that farm management can be. So we work with that farmer, with the field agent.
No, I think well, you should show the data of nitrous oxide and then leaching also. Yeah, even we did a lot of work in leaching, and all the time nitrogen leaching is higher in AWD than in conventional rice. There are a lot of chemistry differences. Anyway, I think you can make all those things, those parameters, and then show which one is working.
Cool. Thanks for sharing.
Okay. Yeah. And a last question before we close the session. Almost on time. Okay. Thanks a lot. Thanks, Nat, for presentation. And well, time for a beer. Thank you very much.
Thanks. Bye-bye.
Bye-bye.
For the modularity discussion, do you have a sense of like if I wanted to take, okay, that's